Okay, these are the video notes for homework number 8. We're starting a new chapter. This is about continuity. Okay, for our first example, we're trying to show you that f of x is continuous everywhere that you can draw it without lifting up your pencil. So it's continuous everywhere except where you have to stop, lift up your pencil in order to keep going, and then you put it back down. So for this example, our function is continuous everywhere except when x is equal to 4. Okay, here's another example. We're going to be continuous all the way until you get to 2. Then we got to lift up our pencil, and then we can put it back down, and then we stop at 6. So this function is not going to be continuous at 2, and is not going to be continuous to the right of 6, because there's no graph to the right of 6. Okay, this function is just going to be continuous everywhere. Now this is the important part. In order for f of x to be continuous at x equals any number, these three conditions must apply. And actually, if you just take the first two conditions and set them equal, you get that third condition. So really all you need is just that third condition. But we're going to go step by step. We're going to look at condition 1, then condition 2, and if those work, then we go to condition 3 to see if it works. Okay, here's our example. We're trying to figure out if f of x is continuous at x equals 2. So first of all, does f of 2 exist? Yes. F of 2 is 10. Second condition, we're checking to see if the limit as x goes to 2 of f of x exists. The limit from the left is 4. The limit from the right is 4. So we would say yes. The limit as x goes to 2 of f of x exists, and it's equal to 4. Now, since the first two conditions worked, we're going to check one last condition, and basically we just want to make sure that those two things are equal to each other. Okay, if you look at that first condition, we got 10. For the second one, the limit was 4. 4 does not equal 10, so it's our third condition that fails. The limit as x goes to 2 of f of x is not equal to f of 2. So we would say no, this function is not continuous at x equals 2. Okay, here's another example. The only thing that's different is there's no point over here. So when we do our first condition, we're going to notice that that fails and we can just go ahead and stop. So our first condition, we want to check, does f of 2 exist? If you look over here, there's no point when x is equal to 2. So that condition fails. And so we would say no, f of x is not continuous at x equals 2 because f of 2 does not exist. Now, all we're talking about is what's happening at x equals 2. That doesn't mean that it's not continuous at other places. Okay, here's another example. Does f of 2 exist? Yes, f of 2 is 4. Does the limit as x goes to 2 of f of x exist? Well, let's check. The limit from the left gives you 4. Limit from the right gives you 4. So we would say yes, it's equal to 4. So now we can check our third step. Does the limit as x goes to 2 of f of x equal f of 2? Yes, they are both equal to 4. So we would say yes, f of x is continuous at x equals 2. Is f of x continuous at x equals negative 4? Again, we check the first condition. Does f of negative 4 exist? Yes, it's equal to 5. Does the limit as x goes to negative 4 of f of x exist? Yes. The limit from the left is 2. The limit from the right is also 2. So we can say that the limit as x goes to negative 4 of f of x is equal to 2. Now we look at the third condition. Are they the same? The limit was 2. The function was 5. But 2 is not equal to 5. So we would say that the limit as x goes to negative 4 of f of x does not equal f of negative 4. So no, f of x is not continuous at x equals negative 4. Here's another example where the first one fails. If the first one fails, you can just go ahead and stop. Does f of negative 4 exist? No. There is no point when x is negative 4. So we're done. We move on. Similar example, but there's no hole in the graph. Does f of negative 4 exist? Yes. F of negative 4 is equal to 2. Does the limit exist? Yes. The limit as x goes to negative 4 of f of x is equal to 2. Now we can go to our third condition. We got 2 for both examples. So the limit as x goes to negative 4 of f of x does equal f of negative 4. So we would say yes, f of x is continuous at x equals negative 4. Here's another simple example. Does f of 0 exist? Yes, it's equal to 1. Does the limit as x goes to 0 of f of x exist? Yes, the limit from the left is 1. Limit from the right is 1. So we can say the limit as x goes to 0 of f of x is equal to 1. Since the first two conditions worked, we can now check the third condition. Are they the same? Yes, the limit as x goes to 0 of f of x is equal to f of 0. They were both 1. So we can say yes, f of x is continuous at x equals 0. This was the example from the beginning. Does f of 4 exist? Yes, it's equal to 0. Does the limit as x goes to 4 of f of x exist? Yes, it's 1. So now we can go to our third condition. We notice that 1 is not equal to 0. So that means the limit as x goes to 4 of f of x is not equal to f of 4. So we would say no, f of x is not continuous at x equals 4. What about if we take the same function and we do the limit as x goes to 0? First thing, does f of 0 exist? Yeah, it's 0. So we're looking at this region here. Does the limit as x goes to 0 of f of x exist? Yes. Limit from the left is 0. Limit from the right is 0. So that limit will equal 0. Okay, now we can go to condition 3. Are they the same? The answer is yes, they're both 0. So the limit as x goes to 0 of f of x does equal f of 0. So we can go ahead and say yes, f of x is continuous at x equals 0. Okay, now we're going to use those three conditions and we're going to check a piecewise function. For the first piecewise function, we're going to have when x is less than 1, you get one function. So that would be this part right here. And when x is greater than or equal to 1, you get some other function. So that would be this part right here. Now by drawing the actual graph of that piecewise function, it's going to make it really easy to see if the function is continuous or not. Okay, let's go ahead and check the three conditions. First condition, does f of 1 exist? So we want to know, is f of x continuous at x equals 1? So we're going to check f of 1. That's our first condition. F of 1 is, well, we have to use this function, so we're going to plug a 1 into ln of x, and we get ln of 1. ln of 1 is 0, so we do get a value, so we'll say yes. F of 1 exists, so our first condition is okay. Second condition, we want to say, does the limit as x goes to 1 of f of x exist? So we got to check the limit from the left, compare it to the limit from the right, and see if we get the same thing. Remember, it's a different function on the left than it is on the right. So when we're doing the limit as x goes to 1, we're going to plug 1 into a different function each time. Okay, so on the left side, it's x squared minus 1. So I'm going to plug a 1 into x squared minus 1, and it gives me 0. On the right side, it's ln of x. So when I'm doing the limit as x goes to 1 from the right, I have to plug into ln of x. When I plug it into ln of x, I get ln of 1. ln of 1 is 0. And because those are the same number, we can say yes, the limit as x goes to 1 of f of x does exist. Now because the first two conditions worked, we can now look at that third condition. Basically we're just saying if we got the same value. Condition 1, we got that f of 1 was 0. Condition 2, we got the limit as x goes to 1 of f of x is equal to 0. So now we want to check, are those the same values? Yes, they are. So we can say that the limit as x goes to 1 of f of x is equal to f of 1. So if we wanted to answer this question, we would say yes, f of x is continuous at x equals 1, and we could just say because all three conditions of continuity were satisfied. Okay, this is our last example. This is another piecewise function. This one's a little bit easier. It says that the function is x squared as long as x is not equal to 1. So that means everywhere else except for x equals 1. Now when x is equal to 1, it's this function. So if you plug a 1 into that function, you get ln of 1, which is 0. So that would be only at that spot. So it's kind of like a point. When x is 1, it's ln of x. Now let's look at the three conditions to see if the function is continuous at x equals 1. First, we have to check f of 1. When I'm checking f of 1, I plug into the function when x is 1. F of 1 is ln of 1, and that's just 0. So yes, f of 1 does exist. It's equal to 0. Now we'll check the second condition. Does the limit as x goes to 1 of f of x exist? Now, because it's the same function on the right as it is on the left, we only have to check one function, and that would be the x squared function. When you plug in a 1 into x squared, you just get 1. So that's just a plug-in limit, so we can see that the limit as x goes to 1, whether it be from the left or from the right, is just going to give you 1. So yes, that limit exists, and it's equal to 1. Now we can look at the third condition because the first two conditions worked. We saw that f of 1 was 0, and we also saw that the limit as x goes to 1 of f of x was equal to 1. And we just want to compare those. Are they the same exact number? No, 1 is not the same as 0. So if we want to answer the question, is f of x continuous at x equals 1? We would say no, f of x is not continuous at x equals 1. And the reason would be the reason that failed. In this case, it'd be condition 3 that failed. So the reason would be because the limit as x goes to 1 of f of x is not equal to f of 1.